welcome to lecture 56. In this lecture, I am discussing about Cohen's theorem on Noetherian rings. Let me start. Just let me start with one corollary to Hilbert basis theorem. Let R be a ring with unity, then R is Noetherian if and only if R of x1, x2 and so on xn, this is Noetherian. Okay. It's a polynomial ring in n variables over R. Okay. So, just simply an application of this follows from Hilbert basis theorem, okay, and by induction also, okay, and by induction on n. If n equal to 1, then we are done. By n equal to 1, then follows from, then it follows from Hilbert basis theorem, okay. And if n greater than or equal to 2, then we can write R of x1, x2 and so on xn, this as R of x1, x2 and so on xn minus 1 adjoint xn, okay. But this ring is Noetherian, right, by induction hypothesis. Therefore, by the n equal to 1 step adjoining xn, this is also a Noetherian ring, then it finishes the proof. So, now let me prove the theorem of Cohen. So, let R be a commutative ring with unity. Then what this theorem says is R is Noetherian ring if and only if every primordial is finitely generated. So, then R is Noetherian if and only if every prime ideal in R is finitely generated. Okay. Now, first let us, this part is easy, right? Why? Because if R is Noetherian, every ideal is finitely generated. Therefore, in particular the prime ideals are finitely generated. So, it is an easy part, I am just leaving. Now, let us look at the reverse part. This is highly non-trivial part. Okay. So, let us assume R is, let us assume every prime ideal of R is, every prime ideal in R is finitely generated. Okay. So, then we need to show that R is a Noetherian ring. Okay. So, for that one, let us consider the following family. Let F, so this is equal to set of all I such that I is contained in R, an ideal such that I is not finitely generated. Okay. I is not finitely generated. We are planning to show that this family is empty. Okay. So, to show that, then we are done. To show that this family F is empty. Suppose it is non-empty. Suppose on the contrary, assume F is non-empty. But R is a Noetherian ring. Okay. Now, let us look at, let tau let T contain, say, subcollection of F, this be any chain in F. Then let us look at T naught. This is union of T. T belongs to tau. This is contained in R. This is an ideal because it is a chain. Because of that, their union, it will become an ideal. And T naught is not finitely generated. Okay. So, otherwise, if T naught is finitely generated, what will happen? If T naught is finitely generated, then T naught belongs to, then T naught is equal to, okay. So, I mean this belongs to tau, this is contained in F, okay. So, but that is contradiction, this is a contradiction because T naught belongs to F, this is a contradiction. Therefore, T naught is an upper bound belongs to F, okay, is an upper bound for tau, okay, upper bound for tau. Therefore, by John's lemma, this family F has a maximal element. Okay, let us say J. Okay, J is a maximal element. So, say J, this belongs to F is a maximal element. Okay, since J is not finitely generated because it is a member of the family F, J cannot be prime ideal. Okay. Why? Because every prime ideal is finitely generated, therefore, J cannot be equal to a prime ideal. That is, implies that there exist elements x and y belongs to R such that x does not belongs to J, comma y does not belongs to J, but if you take the product x y, this belongs to J. Okay. So, now let us look at J. This is strictly contained in J plus R y, and of course, J is also strictly contained in J plus R x. Okay. Why? Because x and y there does not belongs to J, because of that, therefore, strictly contains J. So, this implies that, let us look at J plus R y, this does not belongs to F, because by maximality of J. Okay. So, that means that J plus R y is finitely generated, right. It is finitely generated. So, let us say J plus R y, so this is equal to generated by y 1, y 2, let us say y r, okay, for some y is, this belongs to J plus R y, okay. And of course, note that if you look at y I times x, so this belongs to x j plus r x y, but x y belongs to j, then this is contained in, whole thing is contained in j, therefore, y I x belongs to j for every I. Okay. So, now each y I belongs to j plus r y, so where, let us take it as y I, this is a I plus alpha I times y. Okay. So, for some ai's belongs to j, alpha i's belongs to r. So 1 less than or equal to I less than or equal to r. Okay. So now let us look at the colon ideal. J colon ry, okay, in the ring R we are taking. So what is this? This is all those z belongs to R such that zy belongs to j. Okay. So now let us look at this. This contains j plus rx. Why? Because xy is in j, therefore this contains this one, but this strictly contains j. Okay. Why? Because since this, the only reason is xy belongs to j. So now this implies that j colon ry, this does not belongs to f. Okay. Why? Because again by maximality of j, that means it is finitely generated. J colon ry is finitely generated, say, so j colon ry, so this is generated by x1, x2 and so on xs. Okay. So now we have xjy. If you look at xjy, so these are all belongs to j, because okay, for some, okay, let us write down, for some xi's belongs to j colon ry. Okay. So then xjy belongs to j for every j from 1, 2 and so on comma s. Now our claim is to show our j is exactly generated by a1, a2, ar comma x1y and so on x s y. Okay. So this part is fine, because each a1, a2, ar, each ai belongs to j, and xi y also in j. Therefore right hand side is contained in the left hand side is fine. We need to show the left hand side is contained in the right hand side, the other inclusion. So for that one, let me take an element a belongs to j, the left hand side. So but j is contained in j plus yr, but j plus yr is generated by y1, y2 and so on comma yr. Okay. So that means that a we can written as summation ci yi I from 1 to r for some ci's belongs to r. Okay. So this means, yeah, this is equal to summation ci yi is ai plus alpha I times y I from 1 to r. I just substituted what are the yi's, expressions for yi's. So those here. Okay. So ai plus alpha I y. So therefore this is equal to this. Now this is summation I from 1 to r ci ai plus summation I from 1 to r alpha I ci alpha I, this into y. Okay. So this means a minus summation I from 1 to r ci ai. So this is equal to summation ci alpha I from 1 to r times y. This belongs to j, because the left hand side, this one a belongs to j and summation ci ai also belongs to j. This belongs to j. This means that summation ci alpha I from 1 to r, this belongs to j colon ry. Okay. This belongs to j colon ry, but j colon ry, this is generated by x1, x2 and so on comma xs. So that means this summation ci alpha I from 1 to r, this we can written as summation certain dj xj j from 1 to s. So therefore our a we started, this is equal to summation ciai I from 1 to r plus summation dj xj y j from 1 to s. So that means that where it belongs, this belongs to a1, a2 and so on comma ar. That is what the first combination is, and the second combination is x1y, x2y and so on xsy. Therefore a belongs to this sum, but what is this? This is precisely our right hand side. Therefore left hand side is contained in the right hand side, therefore they are equal. The reverse inclusion is already we argued, so therefore they are equal. So this therefore J is finitely generated, because it is generated by a1 a2 ar comma x1 y and so on xsy, therefore it is finitely generated. But this is a contradiction, because this J belongs to the family F, and J is a maximal element here. Therefore our contradiction we arrived, because if we assumed F is non-empty, that means that our family F must be empty. Therefore R is a Noetherian ring. Means every ideal in R is finitely generated, therefore it is a Noetherian ring. This finishes the proof of the Cohen's theorem. So now let us prove one more theorem. So in a commutative Noetherian ring with unity, of course with unity is already there, every ideal contains a product of prime ideals. Every ideal contains a product of prime ideals. So it is also very interesting characterization of Noetherian rings, commutative Noetherian rings. Okay, so for that one let me start. Let R be a commutative Noetherian ring. Okay. Okay. So let us consider the following family F. So this is, okay, maybe I will write down below. So let F, so this is equal to all ideals, the collection of all ideals I in R such that I does not contain any product of prime ideals. I does not contain any product of prime ideals. So let us look at this family F. We want to show that this family F is empty. Suppose F is non-empty. Suppose our family F, this is non-empty. Then this F has a maximal element. J, because R is Noetherian. Because R is a Noetherian ring, therefore F has a maximal element J. So then this forces that J is not a prime ideal. Why? Because if it is a prime ideal, then J contains product of prime ideals is trivial, that is, so therefore J cannot be a prime ideal. So, this implies that there exist elements x and y belongs to R, x and y belongs to R such that x, y the product belongs to J, but x does not belongs to J and y also does not belongs to J. Okay. So, now let us look at I1. This is the ideal J plus Rx and I2 is the ideal J plus Ry. Then I is then J is contained in I1 intersection I2. Okay. And this J is not equal to I1 and this J is also not equal to I2. Okay. Why? Because x does not belongs to J. Therefore, by maximality of J, this J cannot be equal to I1, J cannot be equal to I2, but J is contained in the intersection. So, now this implies that this I1 and I2 there does not belongs to F, okay, since by maximality of I. So, the maximality of J. So, therefore, I1 comma I2 contains a product of prime ideals. Okay. I1, I2, because I1 does not belongs to F, I2 does not belongs to F. Therefore, this implies that if you just look at the product I1 and I2, this contains a product of prime ideals. Okay. But I1 into I2, so what is that? This is J plus Rx plus into the product with J plus Ry. So, this is simply J plus x y Rx y, but this is same as J. Okay. That means that J does not belongs to F, but this is a contradiction, right, because J belongs to F. Therefore, we got this contradiction because we assume that F is a non-empty family, hence the family F must be an empty family. So, that means that every ideal contains a product of prime ideals. This finishes the proof of the